In this video, I'm again going to show you a few programming tricks in C using the AVR and specifically the ATMEGA328P. Let me switch over to the slides. I am still making use of the slides from Zephyr Naimi. In this specific video, I'm not using all of them, but I'm using the majority of them. So let's start by scrolling down to this. What will be the topics? I'm going to look at also at data types, at time delays, I/O programming in C, logic operators in C, and data serialization in C. So if you go to the next slide, first of all, let's just quickly talk about languages. We are working in this specific video, we are focusing on C language. It's a high-level language, and it's easy to develop and update. Those are the advantages. It's got an acceptable performance. What that means is the time execution of certain statements are acceptable, and it's quite fast. It's easy to develop and update, and it is portable, meaning you can move it from one microcontroller in, let's say, the AVR series to another one. But to be quite honest, you can actually also port this from one microcontroller to another with adding slight changes. If you do assembly language, that is not possible. But in C, you can actually port, I would say, around about 70–80% of a C language from one microcontroller to another one, and just the other 30% needs to be changed. Low-level languages, they are high performance in terms of time, but they are not portable. You cannot take a program from an AVR and try and port that to a PIC, for instance, or an 8051. It cannot be done. This is just a simple C program where you write a program to calculate the sum of these numbers, 1, 3, up to 13 and 15. In this specific instance here, it was actually set, make use of an unsigned int, but to be quite honest, I wouldn't have done that, because by using an integer, you're actually using 2 bytes or 16 bits, which is not necessary for this specific application. You could have used a char here, which will only make use of 1 byte, which is less data or less space that you're wasting. So let's go over to the next slide. In this specific case, it says write an AVR program to send this specific value to port D. So the first thing you have to do is you must set up the direction to become an output, and this is how it's done. In previous videos I've explained this. DDR-D must be 0 hex FF, basically all ones. If you make it all ones, it means it will be an output, and sorry, and then you can write out the value of hex AA to port D. Let's go to the next slide. In this specific example, it says write an AVR program to calculate pin B and pin C and send the result to port D. So it's quite logic that port D will be an output, and port B will be an input, and port C will be an input. That's why you will read the values on pin B and pin C. So here it is. Port D is all zeros. You set the data direction up for all zeros, meaning it's all inputs. The same with port C, it's all inputs, and port D, all ones, meaning they are all output pins. And that's where you can add then in your while one loop. There must always be a while one loop. Port D, which is now the output, is what you see on port B, and you'll basically see it on pin B, of course. You collect that value from port B, you collect this value from port C, you will see it in the pin registers, and that is then transferred, the sum is transferred to port D. So in this specific microcontroller, the AVR, there are a few data types, and it says here, please use unsigned whenever you can. Especially if it's a positive number, use unsigned. I normally only use unsigned and very rarely use signed, but we'll talk about that just now. It also says use unsigned char instead of unsigned int, like I've said in the previous example, because if you use a char, it's 8 bits, and if you use an integer or an int as it's specified here, it's 16 bits, which in many cases is a waste of space. So an unsigned char, that's one of the first ones we see here. That's also the one especially in embedded systems, which will be used the most. Unsigned char is from 0 to 255, so if you've got a value of 300, it cannot fit into an unsigned char. You have to make use of the next size, which will be an unsigned int, for instance. So if you do not put anything, if you just put char, it actually means it is a signed char. So this is why it says rather use unsigned whenever you can. So start by getting used to that method. So you can use char, but I would rather prefer to use unsigned char, because if you use char, it actually means signed char. And signed means it's going from minus 128 up to plus 127, which means you only have in your magnitude of your byte, 7 bits will be the magnitude indicating the size, and the most significant bit will indicate if it's a positive value or a negative value. If it's a 1, the most significant bit, it's a negative value. If it's a 0, it's a positive value. The next size, which is also one that you will constantly use, is unsigned int, which is a 16-bit, and it goes from 0 to 65535. So in total, numbers of 65536, because 0 can also be added. And again, if you use int or signed int, it is from minus 32,000 up to around about plus 32,000. Unsigned long, as you can see, unsigned again, it's only positive values from 0 up to around about 4 billion, a little bit more than 4 billion. If you use a long, you can go from minus around about 2 billion to positive 2 billion. You can also make use of a float, which is going from, let's say, minus 1.17 exponent minus 38 to plus 3.4 exponent 38, or vice versa. And the same with a double. These two basically give you exactly the same. So in rare occasions you can make use of a float, which is possible, but in, I want to say, all cases you're definitely going to make use of at least an unsigned char or an unsigned int, because those are the ones that's been used in C quite often. Let's look at this, the data types. It's continuing. A char will take 1 byte. An integer will take 2 bytes. An unsigned int will also take 2 bytes. A long will take 4 bytes. What's the difference between int and unsigned int? I've already mentioned that an int, if you do not say anything in front of int, it's actually a signed int, and you only get positive and negative values. In this specific case, it says accessing I/O registers. We will in all programs always include this AVR/IO.h, the header file. In this specific case, the port D will be made all ones. It means it's an output. All pins are outputs, and in this specific case, it's just using a for loop, counting from 0 to 9, and that is displayed on port D. So in time delays, like with any microcontroller, you can make use of a for loop to give you a time delay. So one can just, in any, you can write down this for loop, and for any compiler it will give you a specific delay. The problem with this type of approach is that you do not know what delay it will give you, because let me just give you an example. On the 8051, if you make use of around about a 12 megahertz crystal, and you use a value in that for loop of 19,000, you get around 1 second delay. But if you use exactly that same for loop in an AVR, you're not going to get 1 second delay. So it's as it says at the bottom here, if you use the for loop, the clock frequency can change your delay duration. So that's the first thing that can change. and the compiler has direct effect on the delay duration. So the one microcontroller will give for this specific value and maybe an X delay, while another microcontroller will give you 0.7x or something like that. So this is not a good way to. It's a trial and error method to get a delay. Rather, on the next slide, we will see in AVR we can use predefined functions which is being declared, which you can declare. So in my previous examples, I've already shown that you must define the frequency of the crystal that you make use of. I'm making use of the Arduino. Well, although I'm making use of Atmel Studio to program, I'm making use of the Arduino as a hardware tool. In that case, I make use of a 16 megahertz crystal. So you just have to define what is the crystal. You can make use of this header file, which is a delay header file. And then what you should do is also, then you can actually start using functions inside this header file, like underscore delay underscore US for microseconds, and this one for milliseconds. So, and again, it's compiler dependent. In some other microcontrollers, you do not have this, this for instance, the header file. So look at this, byte size I/O programming. So you can address a byte. In this specific case, I'm addressing a byte. I'm saying the data direction must be all ones, but the point is, it's addressing a byte. Here you address a byte, giving a certain value to it. And the same here, you're addressing a byte. Different compilers have different syntax for bit manipulations. So bit manipulations is the next thing to do. For instance, in a 8051, it is possible to, it's quite easy to set a bit or clear a bit. But as it says here, it's better to use bitwise logical operators. So let's look at the bitwise logical operators. And we will see here that if I use and this is my input A and B, if I AND 0 and 0, it's going to be zeros. Whenever you see a 0, there's a 0. There's a 0, there's a 0. Only when it's 1 and 1, you'll see a 1. If you OR, if there's a 1 on A or B, like there's a 1 on B, it will be a 1 on, the output will be a 1. A 1 on A, output will be a 1. 1 or 1, it will be a 1. And only when it's 0 and 0, you'll get a 0 if you OR them. Exclusive OR, if you've got 0 and 0, on A and B, it's going to be a 0. When they are different, like here and here, it will be 1 and 1. And if they are the same again, it's going to be 0. So where they are the same, they're zeros. Like for instance, 0, 0 and 1, 1, 0 here, 0 there. And then where they are different, it's going to be a 1 and a 1. And what you see here is the inverter. So you can actually invert a bit, like in this case, Y is the inverse of bit B. So if B is a 0 here, B will be a 1 there. B is a 1 there, it will be a 0 there. And of course, they could have written down a 1 here because of that 0, and because of that 1, a 1 there also. So if you look at the operation, this is just for bits. So if you look at the operations in a byte, it's still bitwise because the bits will be ANDed in this case. So this is an AND. And if you look at when you start ANDing a byte like this, and you're ANDing it with zeros, that the first, well, from left to right, that's 7 there. It will make sure that whatever stats here at the top will basically I'm not referring to this one sitting on the right hand side. The rest of them will all be definite. It will be forced to become zeros. So the 7 most significant bits will all, because of these zeros sitting here, the output will definitely be all zeros, as you can see there. But where you AND a bit, in this specific case, this least significant bit, it is a 1, and if you AND it with a 1, it will become a 1. So ANDing function is in actual fact, it's forcing certain bits to become zeros. If you start ORing, you will see that if I make use of the same constant value, the zeros has got no effect. So the top part, the 7-bit sitting here will definitely remain the same. But if you OR something with a 1, if this specific 1 sitting here was a 0, and it's ORed with this 1, it would have forced this one to become a 1. So when you OR with a 1, this bit will change to a definite 1. But if you AND with a 0, these bits will definitely be forced to become a 0. All these bits here will become zeros at the end. And then if you take this inverter stage here, whatever you see here, all the bits will be inverted. So those 3 1s becomes 3 zeros, that 0 become a 1, etc. The shift operator, if you've got this shift to the right, it actually means, if you look at this thing here, if you've got this as a constant, and you shift them to the right, it means these 3 bits will be shifted 3 bits to the right, and zeros will shift in. So there you see it, zeros are shifted in, but these 3 bits will be shifted to the right hand side. This the 3 that you see here. In this specific case, if you say move left, this is what this shift operator is. Be shifted left by 2 positions. This 1 will be moved 1, 2, and it will actually go and sit there, as you can see here. There it is. And in will shift to zeros, of course. Now, it's also quite nice to set a bit in a byte to a 1. Set means make 1. We can make use of the OR operator to set a bit of a byte to a 1. So in this specific case, you've got some value sitting here. It's just showing X's, but you've got some value sitting there. And if you OR it, this is bit number 4, because this is bit number 0. This first one is bit number 0. This is bit number 1. This is bit number 2, 3, and 4. So if you OR this value here with this value here, we are only going to look at this specific one. So if you do that, whatever is this X will be forced to become a 1 because of this ORing it with a 1. The rest, this 3X is sitting here, will be the same there. If it was 101, it will still remain 101, etc. So a 1 forces the output to become a 1, while this, what you see there, is just what you see here. Another way of writing this, and again in some of my other videos I've shown that, you can also, what you see here, 1 smaller than 4, is actually saying in bit position number 4 there's a 1. So this is what you see here. This is exactly the same as what you see there. So the result will actually be then, of course, exactly the same. What you see there is the same as what you see there. Another way to write this in C is to make use of this method of writing it. Port B is actually what this means. Port B is the previous value of port B, which is ORed, that is ORed with bit number 4 being a 1. This is what it means. So what you see here is the C version of what is happening here. So what's going to happen in this specific case is that you will set, meaning make 1, bit number 4, which is the 5th bit of port B. So this is bit 0, 1, 2, 3, 4, but it's the 5th. This is the first bit, the 2nd, 3rd, 4th, the 5th bit, but we number them from 0, of course. So this is how we basically can make sure that in port B, bit number 4 is made a 1 by ORing it. So this is an easy way, and it works in all compilers. Let's look at the next one. So you can set a bit in a byte to become a 1. Now we can also go and clear a bit in a byte to a 0. Clear means make 0. And for that, we use the AND operator to make sure it becomes a 0. So in reality, what you want to do is you've got a certain byte there, and you want to make sure that this bit sitting here is forced to become a 0. So what you will do is you'll AND that specific bit, or this whole byte rather, with this value here, but making sure that that bit is ANDed with a 0. So that forces the output to become a 0 while it's not doing anything for those 3 bits. It remains the same, and anything for those 4 bits, it also remains the same here. Now another way if you look at this, another way to write that is by saying, but as we've seen before, remember what we said in the previous slide. We said that this 1 smaller than 4 is actually, the 4th bit is a 1. So, and the rest of them are all zeros. So if you take the inverse of that whole byte, what you see is actually, what you see here is the same as what you see here. So this is just saying, listen, bit number 4 of a constant is actually, you do this, it's a 0. That's basically what it means, while the rest are all 1s. So doing this is the way that we're going to use it in C, because it's the same as what we have here. And the result, as you can see here, is the same as what you see there. So it's exactly the same result, which is actually an easy way then to make sure that a specific bit this could have been port B. That makes sure that bit number 4 in port B is definitely forced to become a 0. And this is also the way that we write this. So we say port B is actually, you must AND that with the position, well, bit number 4 being a 0. That's basically what it means. So AND port B with bit number 4 being a 0. And that will force bit number 4 in port B to become a 0. Next slide. Let's see what's happening there. Now it's also possible to check a bit in a byte. You can actually determine, is it a 1 or is it a 0? So in this specific case here, what you can do is, if I want to check bit number 4, you can AND it with this. And if bit number 4 was a 0, that will be a 0, meaning everything will be a 0, because the rest is also zeros. If bit number 4 was a 1, if x was a 1, this would be a 1. This is why we put x there, because if you AND specifically with a 1, it depends on x what the outcome will be. So it's, if bit number 4 is a 1, that will be a 1, and this whole value will be, well, a value bigger than 1. It could be a value equal to 1 if we were talking about this bit here, the least significant bit. But yes, if this bit is a 0, then everything will be a 0. So we can actually test, is it a 0 or is it not 0? So another way to basically get to this exact same value is, again, we say, let's make bit number 4 a 1, and then AND this, whatever it is, AND it, a port for instance, with bit number 4 being a 1. And again, we'll get a certain answer. So there are actually 3 ways to test this. If you can say, the easiest way is actually just to say, if pin C, so it's actually taking the value of pin C, this could have been pin C, what you see there actually could be pin C, and you AND that with, and then it's actually checking bit number 4, because this is a constant value. It's checking bit number 4 in pin C. So if it's a high, this value will be true, and you can execute something else. You can execute something else which indicates that bit is a 0. So this is another way. So it's testing pin C, and it's ANDing it again with a bit number 4 position, being a 1, and it's testing, is it 0 or is it not 0? And the same with this thing. It's testing, is it bigger than or equal to 1? So in this case, is it equal to or not equal to 0, meaning it's 1 or higher, and this one also says it's actually 1 or higher. So it's just different methods of writing the same thing. So let's go to the next slide. So the memory types in AVR, you get flash memory, which is not deleted when the power is off. It's quite big in size. In the ATMEGA328P, it's 32K. and it's suitable to place codes in there, tables, fixed data, etc. EEPROM, in previous videos I've also shown what EEPROM is. It's not deleted when power is off. It's not so big in size. Again, in the case of the ATMEGA328P, it is 1K, and it's suitable for small data that may be modified but should not be lost when power is off. So if you've got a settings value, this is where you will store it, because settings are not changed often, but it can be changed. And then RAM, of course, it is deleted when power is switched off, and it's suitable to store data that we want to manipulate, because we have fast access to read or modify them. Okay, if I look at this slide, I'm going to make another video. I'll also post this video how to access flash memory. In other words, how to use the flash memory to actually store data. And I've already made a video before where I showed how you can access EEPROM. It's quite easy to access EEPROM. There are two methods. You can access it by making use of specifying the address, or you can access it by making use of a header file. But for now, this is where I will stop with the different types of memory in AVR. So you can have a look at my YouTube channel to find this EEPROM, access to the EEPROM, and also access to flash. Thank you.